SwayamPrabha. Digital India. Educated India.
Welcome back. So, we were discussing the steady flow devices. We will continue our discussion in this particular lecture. Particularly, we will take up throttling valves, mixtures, heaters and heat exchanger. Okay. So, let us start with the throttling valves. So, throttling valve is basically any kind of flow restricting device, and thus it cause significant pressure drop in the fluid. So, there is a difference compared with respect to turbine, and the turbine particularly do not lead to significant change in the in temperature, but in case of a throttling valves, the pressure drop in the fluid is often accompanied by a large drop in temperature, and this is the reason that throttling valves are commonly used in refrigeration, air conditioning applications. There are different kind of throttling valves. You can have adjustable valves, you can have a porous plug based or a simple capillary tube. Okay, these are all examples of throttling valves. So, let us look at how we are going to apply simple energy balance. The material balance is very obvious that since the mass flow rate should remain constant for the case of steady flow conditions. So, what about the energy balance here? So, we will be considering Q to be 0, and the reason for that is considering the device is very small, and hence we will be considering such a flow adiabatic. The work would be also 0, and as well as your change in the potential energy and kinetic energy to be 0. Okay, and thus your m theta inlet should be same as m theta outlet, and since your kinetic energy and potential energy is 0, so you have this condition, and considering that m dot is same for the inlet and outlet. So, you have for the throttling valve a simple enthalpy, a constant enthalpy process. So, throttling valve essentially means that the enthalpies are same. You have internal energy plus the flow energy term as a part of the enthalpy. They can interchange, but the total value should remain constant. Okay, so if you consider idle gas, now we know that for the case of idle gas, enthalpy is only a function of temperature, and hence if enthalpy is constant, which means the temperature is constant for idle gas throughout this valve. And during this particular throttling process, enthalpy of a fluid, as I said, can remain constant, but internal and flow energy may convert each other. So, that means the flow energy can lose some energy, and the internal energy can gain through during this process. That is some aspect which we are going to look at in an example. Okay, so let us take this and understand a bit more about throttling valve. So, this is an example of refrigerant, okay, which enters this capillary tube of a refrigerator at a condition which is saturated liquid at 0.8 megapascal and is throttled to a pressure of 0.12 megapascal. So, there is a huge jump in the pressure, okay, and hence your temperature should also change. Determine the quality of the refrigerant at the final state and the temperature drop during this process. Okay. So, we will consider this as 1 and this is as 2. Now, we will start with the temperature at 1. 1 is at saturated liquid. Okay. Okay, so this is equivalent to Tsat at 0.8 megapascal, okay, which is nothing but 31.31 degrees C from the table. So, this table is here given in A12, and this is your 0.8 megapascal. This is your saturation temperature corresponding to 800 kilopascal. Now, T as saturation is given. Now, what we are going to assume, okay, what we have to consider now is the enthalpy, because we know the enthalpy is constant, which essentially means H1 should be equal to S2, and H1 is nothing but HF, because this is a saturated liquid, okay, at 0.8 megapascal. Okay, so the table tells you this is nothing but 95.48. So, this is your 95.48 kilojoules per kg. Okay. Now, what about your P2? What about your condition at 2 here? So, because the question being asked is the quality, which means there is some change in the state. So, let us look at it whether there is some vaporization which during this process. So, let us look at first P2. What is the P2 here? P2 is your 0.12 megapascal. okay, and H2 is nothing but H1. So the corresponding Tsat at P2 is Tsat at 0.12 megapascal is minus 22.32. So this is nothing but minus 22.32 degree Celsius, and the corresponding HF at this pressures can be obtained here. HF is 22.47 and saturated vapor is 236.99. Since H is constant and H1 is 95.48, this means it lies between these 2 points. So as I said, HF is 22.47 and Hg is 236.99. So our H2, which is nothing but H1, is greater than HF and less than Hg, okay, at of course 0.12 megapascal, which essentially means that since H lies between the fluid and the gas enthalpies, the state at exit would be saturated vapor liquid conditions. So there would be a quality involved of the vapor. So we can calculate the quality X2, which is nothing but H2 minus HF by HFG, and this, if you plug in this value, and HFG is nothing which is this HFG. So if you plug in the value comes out to be 0.340. Okay, this is the quality. So that was the question, that we had to find the quality of the refrigerant at the final state. So this is the quality. What about the temperature drop? So let's find the temperature drop. So what would be the state T2 of the final state? T2 nothing but T2 is just T saturation at P2, because the fact that the final state is at saturation vapor liquid condition, and hence T2 is nothing but your minus 22.32 degrees Celsius. Okay. Thus your change in the temperature delta T, or the temperature drop, is T2 minus T1, which is nothing but minus 22.32 minus 31.31 degrees Celsius, which is minus 53.63 degrees Celsius. So it's very clear that there is a significant drop in the temperature, and the saturated liquid vaporized. The energy to vaporize, it takes it from its own enthalpy. Okay, that's something which is quite interesting. Okay, because the energy required is not taken from any specific external source, but it changes its own state through this particular capillary tube and make use of it for vaporizing from a saturated liquid to saturated vapor liquid conditions. Okay, so now we are going to take another device, and this is your mixing chamber. This is a common operational device which you can see normal at different like hotels, household conditions. This example is an ordinary shower. Okay, so you have a mixing of a hot and cold leading to average temperature water flow, and this is called mixing chamber. Okay, where basically you have a direct contact. You are making use of hot and cold fluid and passing it, that means mixing them physically. Okay, so there is a heat transfer from, of course, the hot to cold. Okay, so you can put this in a schematic form. This is a simple mixing chamber. Okay, here the mixing chamber could be this elbow, but here we can represent in this form. So this is your two inlet fluids, one at 60 degrees Celsius and one is 10 degrees Celsius, and is mixing at certain pressure, and the outlet stream has a specific temperature. Okay, so based on simple mass balance, you can clearly show that this will be M1 plus M2 is equal to M3, and considering this to be a steady flow device, so you will have this condition which is very clear. Okay, you can also come up with the energy balance here. Now considering steady flow, we now are well aware that this will be the case for steady flow. Now we will be considering that there is no heat supply to it. Okay, so that means Q dot is 0, and as well as the work, there is no work done by the system, and we will be assuming that the changes in the kinetic energy, potential energy to be 0. In that case, your simple energy balance would be your summation m theta inlet is equal to summation m theta outlet, or in a generalized form it will be simple. For the case of this system where your kinetic energy and potential energies are 0, or the changes are 0, your H inlet should be equal to mH outlet. Okay, and this is what is written here. So this is a simple energy balance for the case of mixing chamber. So we can take another device. Now in this case, which is a heat exchanger, this device allows the heat transfer without direct contact of the fluids. So, a generalized definition is these are the device where two moving fluid stream exchange heat without mixing. It does the same operation, but it does not allow the physical mixing of the two fluids for the heat transfer. And this is commonly used in various industry, and they can come up with a different design. So, this is a simple analysis of the heat exchanger. For example, here you can see this is let us say a fluid A passing through a pipe, and then you have another fluid through this control volume. And if you consider the control volume as a dashed line here, okay, there is no additional heat transfer at the boundary from the surrounding to this control volume. It happens within this control volume. So, thus your overall control volume heat exchange would be 0. But on the other hand, if you come up with the control volume boundary as a within the pipe of fluid A, then there is a heat transfer from the outside of this control volume, that is from B to A, okay, and thus your QCV is not equal to 0. So, it depends on the how you come up with your control volume, okay, and depending on the control volume your heat exchange may be 0 or non-zero. Okay, that is the heat transfer associated with a heat exchanger example. So, we will try to do some example in order to get a little more insight to this. So, this example is a refrigerant which is to be cooled by water in a condenser, and the refrigerant enters the condenser with a mass flow rate of 6 kg per minute. So, which essentially means you have a refrigerant 134A, okay, which is at 70 degrees Celsius 1 megapascal, and it exits at 4 with at 35 degrees Celsius. Water enters at 15 degrees Celsius at 300 kilopascal, and it exits at 25 degrees Celsius. Okay. So, the water heats up a bit, and there is a drop in temperature in the refrigerant. So, the mass flow rate of refrigerant is given, and what we have to do is we have to neglect any pressure drop and determine the mass flow rate of the cooling water required. So, we can do a simple mass balance. Based on the mass balance being this two fluid water and refrigerant, they do not mix, and hence the mass flow rate should remain constant, which essentially means that the mass flow rate for the refrigerant at the inlet condition should be same as outlet condition, and for the same is true for the case of water. So, we can write that, you can say that M1 dot is equal to M2 dot, and that will be, let us say, water flow rate, and M3 dot is nothing but M4 dot, that will be your MR, that is the flow rate for the refrigerant. Okay. So, this is your simple mass balance. Now, we can write your energy balance, and considering is a steady flow device, we can write this as simply E in dot equal to E in out. Okay. Or in other word, your Q in plus W in for the case of inlet streams is equal to Q out plus W out outlet. The heat we are assuming is, we consider it to be a complete control volume. Okay. Okay. In that case, your Q dot and W dot should be 0, and assuming the kinetic energy and potential energy to be 0, this can be simply written as M dot H inlet should be equal to M dot H outlet. Okay. Or in other word, the inlet are 1 and 3. So, we can write M1 H1 plus M3 H3, this is same as M2 H2 plus M4 H4. Now, M1 is equal to M2, this is what we are saying is MW. So, we can rewrite as okay, we can take the common terms and we can rewrite this energy balance in this form. Okay. Now, what is the next thing to do is to find out this enthalpies, and for that we have to make use of lots of table. Let me just summarize the procedure to solve the rest of the problem. Now, the first important thing is to look at whether the given conditions which are given for the water, is it in a compressed state or superheated state or saturated liquid state. So, the temperature given is 25 and 15 degrees Celsius at 300 kilopascal. Okay, and since there is no pressure drop, so we are assuming that this 300 kilopascal remains same across the end, that means for both the inlet and the outlet condition. So at 300 kilopascal, your Tsat for water is 133.52 degrees Celsius. The temperature which is given to us is much less than Tsat. So thus we are going to consider this to be a compressed liquid. So in that case we can consider H1 to be simply the saturated fluid condition at 15 degrees Celsius and H2 at HF at 25 degrees Celsius. Now this information you can get it from table A4, and these values are 62.982 kilojoules per kg, and this is 104.83 kilojoules per kg. So the water is known. Now what about your refrigerant? For that you have to look at the tables like A13 and A11. So if you look at your conditions of refrigerant, P3 is at 1 megapascal and T3 is 70 degrees Celsius. So these are the conditions based on the A13 will tell you that this is a superheated vapor condition, and hence you can take the value as 3 from the table A13, which comes out to be 303.87. Okay, similarly you can find P4. Okay, and this will be your compressed case for the case of your refrigerant. Okay, so this is your compressed and this is your H4 is okay. Now you plug in this value here, okay, in this equation, you will obtain MW. So that was the question which we wanted to solve. You can also try to find out what is the effective heat transfer in this system by taking a specific control volume. So you can also try to solve this problem of heat transfer rate from the refrigerant to the water by applying a simple energy balance. Okay, so for this specific case here, you can write your QW in So what we have done is that we have specifically considered this control volume in order to find the heat transfer from the refrigerant to the water, and thus this dashed line represents the control volume. You apply the same energy balance equation, but now you have to consider this QW in here, okay, which is nothing but QR out, and this terms related to flow energies. Now, so based on this, you already have MW and you have the values of H2 and H1 from your previous slides here. So this value turns out to be 1218 kilojoules per minute. Okay. You can also consider not just this control volume, but a control volume which encompasses the water only and obtain the same expressions. So this was a simple exercise for making use of the heat exchanger to solve problems related to based on the mass balance, energy balance. And in the next lecture, we will be considering pipe and deck flow followed by your unsteady flow process, and that will be the end of this particular module. Okay, so see you in the next lecture.